Hello everyone. In this video, I explain the morphological effects that occur after the construction of a secondary channel. We consider the situation under subcritical flow. The widening of the main channel has a similar effect, so it is also included in this explanation. The first part explains the effects immediately after construction of the intervention. The second part describes the new state of morphological equilibrium. Part 2. We consider the case of a river in equilibrium, that is, with uniform flow. The river has a rectangular cross-section with width b. The river carries an amount of water Q and an amount of sand S per second. At t equals 0, a secondary channel is built, for example, for the development of nature. Water is extracted. It is assumed that sand does not enter the secondary channel. The width b and the sediment transport S do not change. Only the flow is reduced in the main channel, between the inlet and the outlet of the secondary channel. How do you draw the new state of morphological equilibrium after the construction of the secondary channel or widening, as time, t, tends to infinity? Step 1. Calculate, or estimate, the equilibrium slope, I1, and the equilibrium depth, H1, in the reach of the intervention. Equations to derive the equilibrium state. Equilibrium is the state in which no further changes occur over time. Slope, water depth, and sediment transport are constant, uniform flow. Using the continuity equation, Chase's formula, and the sediment transport formula, the equilibrium state, that is, equilibrium slope and equilibrium depth, can be determined. We assume a power formula for the sediment transport formula. For example, in the Engelund-Hansen formula, the power is equal to 5. When the new equilibrium is reached, the bed level is stable, no erosion or sedimentation takes place. This happens when sediment transport is constant along the length of the river. In other words, the sediment transport in the main channel in the reach of the intervention that we call S1 is equal to the sediment transport upstream or downstream S0. Next, I explain how the new slope I1 and water depth H1 are obtained by applying these formulas for the case of a secondary channel. In a similar way, you can derive the formulas in the case of a widening of the river bed. Applying the transport formula that is a function of velocity, it is determined that the velocity U1 in the reach of the intervention must be equal to the velocity downstream and upstream of it, since the river width is constant. To obtain I1, we apply the Chase's formula. Next, I1 is determined as a function of the original slope I0 and the discharges Q0 and Q1. To obtain H1, we apply the Chase's formula in the same way as with the determination of the slope I1. Next, H1 is determined as a function of the original depth H0 and the discharges Q0 and Q1. H1 can also be calculated with Chase's formula since you know I1. So you can check that you get the same value. Summarizing, there are two formulas for the equilibrium conditions, for the slope and for the water depth. Subscript 0 is the initial equilibrium state and subscript 1 is the new equilibrium state with the intervention. Q is the water discharge. B is the river width. I is the slope. H is the water depth. N is the power in the sediment transport formula. For example, for the Engelund-Hansen formula, N equals 5. For the case of a secondary channel, the new equilibrium state depends on the initial condition and the relationship between water discharges. The smaller Q1 is, the greater the slope. The opposite applies to water depth, the smaller Q1, the smaller H1. For a secondary channel, Q1 is less than Q0. For a widening, B1 is greater than B0. According to the equilibrium formula, I1 is then greater than I0 and H1 is less than H0. Step 2. Draw the water levels in the new equilibrium state. Time tends to infinity. In the downstream part of the river, the discharge and transport of sediments do not change. There the initial equilibrium state I0 and H0 will continue to prevail. In the reach of the intervention, the water level has a constant slope I1. I1 is greater than I0. The slope line should be drawn from downstream, the end of the intervention, upstream to the beginning of the intervention. The full discharge is present upstream of the secondary channel. We draw the slope line from the beginning of the intervention in an upstream direction with slope I0. Step 3. Draw the new equilibrium depth H1 in the intervention reach. The equilibrium depth is drawn down from the water surface. Step 4. Draw the bed levels in the reach of the intervention. Step 5. Draw the original equilibrium depth H0 upstream of the intervention reach. Upstream of the intervention, the initial equilibrium depth H0 is applied. The equilibrium depth is drawn down from the water surface. Step 6. Draw the bed levels upstream of the intervention. What is the long-term morphological effect in the reach and upstream of the intervention? Time tends to infinity. The new bed level is above the initial bed level. Sedimentation occurs in the reach and upstream of the intervention. References. End of Part 2. For more information or questions, please contact info@blueseddynamics.com.